So, do you feel like you have a lot of resources in this class?
Yeah.
Too many? Some. Alright, so we have one more resource. We have Jillian here. She is a former fantastic student from our class last year, and she wanted to be involved in mentorship, so I asked if she'd be willing to come and be a facilitator in our class. So she will be here on and off in our class, helping answer questions, just like Ms. Carol and myself. So if you have questions, anytime you raise your hand and are not quite sure what to do, or she might be walking around anyway, then just make sure that any one of us, you can ask us questions to kind of move in the right direction. So let's go ahead and get rolling. You guys completed a workshop on Friday that this is an excerpt from. So jog your memory. Frequency is BC. Alright, so how did you guys, I want to hear from Jose. How did you look at all of these and determine which one has the strongest intermolecular forces?
Which ones would make hydrogen bonds with the same type?
Which were what, sorry?
Which one would make hydrogen bonds?
Which ones were capable of hydrogen bonding? Okay?
And also the link ones. And like checking out which ones have the strong side.
Great, so two different ways to look at the same problem. One is, which one is capable of doing the strongest intermolecular force? And you said hydrogen bonding is what you picked out. So I have a question. What makes something a ketone? It has a carbonyl group. So I'm going to draw in, what's going on here? Oh no, I need to connect my pencil. Can you off that for a second? Okay, so a carbonyl is something that has a carbon double bonded to an oxygen. Is that the entire definition of a carbonyl? Or a ketone, sorry.
Yes.
That's a carbonyl.
These two methyl groups are R groups.
Okay, so there's a whole bunch of different things. We can have an OH. Is that a ketone?
No, it's carboxylic acid.
So we have a carboxylic acid. So a C double bond to O, that's really important because whenever we see that there's a polar bond there. So that gives us some idea of the property. But if it's connected to an OH, that's incredibly different than if it's connected to an H, which is an aldehyde, versus if it's connected to a carbon on each side. So a ketone means carbonyl, C double bond to O, with a carbon on either side. That means it has one polar bond, as opposed to carboxylic acid that has 3 polar bonds, or an aldehyde that just has less space that it takes up. Okay, so if we look at the ketones in the yellow box, what makes an alcohol? Leah, what's an alcohol?
Can't really say OH or hydrogen bonding.
So it's something that has an OH attached to it, but this has an OH attached to it as well. Is this an alcohol? Megan? Is the thing in blue an alcohol? There's one way to infuriate me on an exam, is to call that an alcohol. Morgan?
Doesn't the acid and hydrogen have to be like one, like molecule together, like a hydroxyl OH?
So we can draw it like this, or we can draw it separate. It implies that there's a covalent bond, either way. What is that functional group that I just drew in blue?
Carboxylic acid.
Carboxylic acid, because it has that C double bond to O, it is a totally different functionality. It functions very differently. Okay, so let's never call that an alcohol. This is an alcohol. Doesn't matter what's attached to the carbon, so long as it's not a carbonyl. That's an alcohol. So back to Jose's point. if we're looking at something, which one of these two is capable of accepting a hydrogen bond? Talk to your neighbor. Can a ketone or an alcohol or both accept a hydrogen bond?
Yeah, so like the oxygen.
So Dan, what do you think? Can one or the other or both accept a hydrogen bond? Alcohol is the only one that can accept hydrogen bond. Do you guys all agree? I don't hear resounding confidence. Taylor?
I think that ketones could because isn't there lone pairs on the carbonyl?
So what do you need to be able to accept a hydrogen bond?
Lone pairs and an electronegative.
A lone pair on a nitrogen, oxygen, or fluorine. Ketone has that. So Demetrius, last class, you were talking about that in an amide backbone, you have a carbonyl. You have a C double bond to O that has lone pairs. That actually allows different parts of the protein to fold on each other and have an electropositive hydrogen interacting with the carbonyl. So yes, a ketone can absolutely accept a hydrogen bond. Can alcohol accept a hydrogen bond? Anna? No. Does everybody agree? Don? Why?
Because it has extra electrons on the oxygen.
So if we go and we fill in the lone pairs for our Lewis structure, we'll see that the oxygen does have 2 lone pairs of electrons. That means it can also accept a hydrogen bond. Can both donate a hydrogen bond? Talk to your group. Decide if both can donate a hydrogen bond. So talk amongst yourselves to try to determine exactly the terminology, what it means, accepting and donating. Join a group, buddy. Okay.
Do I need to be more,
No, I just need to see you guys talking, so I'm giving you a hard time.
They
okay.
have hydrogen, and they go to another, like, more electronegative.
You said donors, right?
Yep.
Okay.
All right, can I hear from Miata? Can they both donate hydrogen bonds? Or which one can if it's not both, or can neither?
Because I think the ketone doesn't need it should be kind of partial positive on the oxygen.
So what do you mean?
I'm not sure.
Brian, you help out? No, not Brian, Chase.
Yeah.
Sorry.
I said that both nicotine and alcohol is good because in alcohol, the OH that each has a like unequal sharing of electrons, so it has a partial positive charge, so it can make a hydrogen bond. Well, it can receive one.
Great. So in order to have a hydrogen bond donor, we absolutely have to have an hydrogen that is very low in electron density, which means it's connected to an oxygen or nitrogen most of the time. So that hydrogen can be a hydrogen bond donor. It means it comes close to a lone pair of electrons on a nitrogen or fluorine, and there's going to be an electrostatic interaction. It's not going to form a new bond, but it's going to come and it's going to be held somewhat closer than if they were just passing by with no electrostatic interactions. Can a ketone do that? There's no electropositive hydrogen. So if you put that ketone in water, it could form hydrogen bonds, but it would only be accepting them. It wouldn't be donating. If you have the alcohol, you don't even need water to form hydrogen bonds. You could just have a whole bunch of alcohols interacting with each other, and they're going to form hydrogen bonds. Okay, so this idea of self interacting with another molecule of itself versus interacting with a molecule of a solvent is something we're going to be exploring with colligative properties, and we're going to be talking about that more in depth today. So, going back to Jose's statement, we know that alcohols can form hydrogen bonds. What about alkanes? What are alkanes? They're nonpolar because they only contain what kinds of bonds? So that's one form of an alkane. Carbons, hydrogens, that's it, totally nonpolar. So it can only do dispersion forces. It can't do any dipole-dipole interactions. It can't do hydrogen bonding, which is a strong dipole-dipole interaction. Okay, so out of these, Jose said, well, I know that one can form hydrogen bonds. So that means that it has stronger intermolecular forces. And then the other way that I really like, he said, is empirical evidence. He said, well, those alcohols have higher boiling points. Why does that mean that they have stronger intermolecular forces? Javante?
Because it requires more energy in order to disrupt the bond.
Disrupt the intermolecular forces. So the idea is that if you have a whole bunch of molecules that are in a liquid form, they're close together, they're feeling the interactions from each other, and in order to get them to be a gas, what do we have to do? Heat it up, which makes them do what? Makes them what? So they don't separate as they're warming up as a liquid, right? What point do they separate? Do they spread out? When they form a gas. Until they form a gas, they're just moving faster. And then all of a sudden they have enough speed, where some of them now are going so fast that they have enough speed to overcome that intermolecular force, and now they can move around as a gas. So if you have a stronger intermolecular force, you need more speed in order to overcome that force to become a gas. So that's something that we're going to be talking about today. I hope everyone was able to complete that. It was technically a physics tour, not a chem tour. But we're talking about a heating curve, and it showed those different interactions. So if you haven't done that, absolutely make sure to do that. I'm going to go through class today, assuming you guys have completed that. So, what was the answer to those alcohols for that last one? I'm guessing that one. Solid. All right. Now I want to know, which one of these three molecules would you predict to be the most water soluble? Talk amongst your group if you're not quite sure. I'll kind of circulate around these. You can guide them, listen to their conversations. What are you guys thinking? Megan, help her out.
I didn't even consider it here.
Oops. Sorry guys, I realized that I flipped the letters on your handout versus on the screen. Let's use the letters on the screen. My bad. Letters on the screen are a different order. What?
Because this one's non-polar, so that won't really dissolve.
Reevaluate that. Okay, let's do a couple more seconds and click in your group's answer or your answer.
Are you guys unsure about A and B? Okay. I'm not sure if the ionic bond would be more soluble.
So go back to what is more attractive. Remember we talked about partial, full, partial, all those kinds of things? So try to think about that, solubility. And you can use some of your examples from your life. What have you seen as far as soluble? All right, we're going to go ahead and close out. Or maybe reveal. Should we do the reveal first before closing out? Ooh. All right, 50-50. Does anyone want to try to convince the class that A or B is going to be more water soluble? Michelle?
I said A because
It's not an ion, it's
negative ions,
an ionic compound.
compound.
Okay?
So the positive magnesium ion will be attracted to, or the oxygen will be attracted to the magnesium ions, and it will separate out from the sulfate, which will be attracted by
So before you go too far down that road, did anybody draw the Lewis structure of sulfate? I have one. Did you guys take this class for the first week? What was the main take-home of all the Lewis structure stuff?
Know the octet rule.
Okay, so know the octet rule. This one doesn't obey the octet rule. But draw the structure because the structure will tell you about the function of the molecule. Anytime you see a polyatomic ion in this class, draw the structure. Immediately draw the structure. If I draw this, what am I missing? So I'm missing a negative charge on that oxygen, and then a magnesium 2+. Does this make it more obvious which one is more water soluble? What's going to be more attracted to water? A partial positive or a full positive? Full positive. What about a partial negative versus a full negative? Okay, so anytime you see an ionic compound, the first thing we should think about is that that will very likely associate with water and it will dissolve immediately. I'm lying to you. That's not completely accurate. We'll be spending some time later in equilibrium talking about how that ionic interaction sometimes is too strong for water to interrupt. That's when we'll talk about solubility rules. We'll be talking about Flint's water system and how they have lead in their water and where that came from and how we can talk about solubility rules to explain that. But for now, anytime you see an ionic compound, we assume that water will completely solvate those ions. Remember, about 6 waters per ion? And that will allow those ionic bonds to then be separate.
Does lead break like every physical law?
So lead doesn't break any physical laws, but the lead in the pipes, there is something added to the water that makes it dissolve that wasn't there before. So the impurity that they found is not actually the source of the water, but it's just something that solubilizes lead more. So it's kind of interesting. So why did everybody pick B?
I picked B because it's the most water soluble because there are so many oxygens that are able to bond to something.
Okay, great. So I wouldn't say able to bond.
Or like willing to. I don't know if the. I'm not sure like how to explain.
So can someone help out? What does looking at that molecule and seeing a whole bunch of oxygens tell us? Shane?
It's polarity.
So that it has most likely polarity. Okay, so it has a higher number of polar bonds. So we can look at this and we can say there's a whole bunch of polar bonds.
The electronegative atoms, so the oxygen and the free nitrogen, can accept more hydrogen bonds.
Great. So I love that. So if it is close to water, water has a hydrogen bond to donate, so it can accept a hydrogen bond. So that means that it has some interactions. If it has no interactions with water, it's not going to dissolve, I promise you. So if we were to put that compound into a grease, then those hydrogen bonds wouldn't matter. We're putting in water. Water's polar. Water has a hydrogen bond donor and accept. So for this question, I absolutely want you guys doing what Kira and Brianna, were saying. And that's to think about, can this accept or donate hydrogen bonds? And so for that reason, I like that B was more popular than C, because C only has the ability to accept one hydrogen bond. It's not very polar. Water is really polar, and that hydrogen bonding between molecules will help them dissolve. But there's something that supersedes that, and that's an ion-dipole interaction. Morgan?
Once I drew the structure for magnesium sulfate, I think a lot more water soluble because it's a smaller molecule, so it's easier to disassociate than that. I don't know if that's called.
That other nasty molecule. It's a terrible molecule, actually. We'll get into what it is in a minute. So anytime you have any ions capable, any ionic bond, so a metal with a nonmetal, and then we should recognize the polyatomic ion as sulfate. So if you guys don't already have them down on our Canvas homepage, there's a link to a set of polyatomic ions. You don't need to memorize every one in the book, but I've very specifically gone through and crossed out the ones you don't need to know. Every other one you need to know the name, structure, and the formula for. Okay, so that's going back to week 1 when we were working with that. So I absolutely agree that anytime we see something that has an ion, we automatically think that's more water soluble than a set of polar molecules. Okay, so I want you guys to tell me, in this nasty molecule, how many polar bonds are there? And go ahead and circle those.
Pretty good.
Oh, right there? I'm sorry, I was taking that shot. I thought you were just playing with me.
It's
More
actually
and more
really
tattoos,
painful
man.
to see.
Let me try it again.
No.
I'm a little worried, you know.
They gave like a presentation and for whatever reason they thought
Oh, you know what, I missed an option.
Yep. Yes, this is the same molecule as in your handout, so you guys can draw on it there. All right, try to finish up in the next 20 seconds. Click in your number of polar bonds that you find in that molecule.
Wait, how do you do this again? I forgot.
Up or down to find numbers.
You have to click the number first.
Got it. We're good. Wait. Oh, so 6.
You're not going to circle them?
Oh, I don't want to circle them until they're right.
You don't have a pencil?
I do, but I forget the other one.
All right, we are going to ask someone in this group to circle them all. Actually, before I do that, I'm going to close out. Let's see what we had. 6, 8, 10, 11, 5, 12. Great. You guys are total agreement. Fantastic. All right. Bueller? Thank you.
Oh, that's heavier than I thought.
You set it
Sorry,
down.
I totally just broke your thing, I think.
2. Okay. Does anybody see any more? Thomas.
That's it.
Okay. So what does that bring us up to?
I think that's 8.
7 or 8? So we have 1, 2, 3, 4, 5, 6, 7, 8. Great. Anything else? Anybody else want to? So remember, this is an idea of we're identifying trends. There are a few things you want to commit to memory, and that's which bonds are very likely to be polar. That is going to save you a lot of time, not only in this class, but any other chemistry class you take. All right, are we good? I hear someone say no. Who said no?
If that N to CHs, is there an N to that C?
And then is that connected to anything? I don't know if that
How many bonds does nitrogen have? So where's the third bond?
Oh, so it goes to here?
That nitrogen is connected to 1, 2, 3. So this one as well?
Oh, no, I missed it.
Okay, so any carbon-nitrogen bond is polar. Not as polar as carbon-oxygen, that's more polar. And that's not as polar as oxygen-hydrogen. So there's different levels. An NH, is that a polar bond? Tatiana, is an NH a polar bond? Yes, we don't have it in this molecule. So the total was 8 plus 1, 2, 3. Is that 11 total? So how many people found 11? 2. All right, guys, you got to step up your game here. So is that just a matter of recognizing that where the line changed directions was a carbon? You want to give your feedback?
The right ones, it's just we made the mistake of not doing it on both sides. We just circled where the oxygens were, so ours was just half.
Great. So it's a matter of polar bonds, not electronegative atoms. Good point. Thanks for pointing that out. So let's see if you guys are doing all right here. What's up, Demonte? CO2 is polar bonds, but it's non-polar.
Oh, non-polar molecule.
Overall, there's a zero net dipole. Closing out. Question?
Yeah, I think I'm missing one still.
Okay, we can catch up on it after class. Oh, it's this one right here. Kirk? You want to ask a question out loud? Follow up afterwards? Next time we're working. Okay, so you guys say that heroin is capable of forming hydrogen bonds with water. Okay, does that mean, let me see what the next question is. Does this directly mean that heroin is water soluble? Talk to your neighbor, talk to your little group, try to figure out whether you think that this is going to be water soluble because it is capable of forming hydrogen bonds with water. What are you doing?
I'm worried about you in class. I've been asking some questions and you haven't seen the strong as you were last semester. Can we catch up in office hours? You'll be able to come tomorrow morning, 8:30 to 10, okay, so maybe you can come just for a couple minutes at least. We can catch up and make sure that you're on the right path. Because I want you to stay on top of your game because I know you're strong.
Katie, I'm going to call on you in a minute. What do you guys think?
Is it, wait, we said no?
What?
I think we were talking, I was thinking that, like, even though it can form some hydrogen bonds in water, that doesn't mean it can be, like, totally soluble, or it could be, like, partially.
Okay.
But, and then you were saying,
What was Alex saying?
Two very, very negative atoms can bond to each other and not be polar.
Okay, so this is asking if it can form hydrogen bonds, it means it does have polar bonds. But yeah, CO2 or oxygen are two examples of this, right? All right, so I'd like to hear from Katie. What are your thoughts on this?
Well, I said it doesn't directly mean it's soluble in water because it has hydrogen bonds. But we also said that heroin can't because of more non-polar bonds.
Great, so I love it that you're looking at the ratio between polar and nonpolar bonds. So it's not just, does it have polar bonds? Okay, the thing can have 20,000 bonds. If two are polar, that doesn't mean it's water soluble. This molecule has some polar bonds. We just circled 11 of them. Were any of them extremely polar? What bonds do we usually think of as being very polar? OH. Specifically an OH attached to a carbonyl, a carboxylic acid. When we see a carboxylic acid, we think that that's an extremely polar functional group, and this doesn't have any of those. So this is kind of the process I want you guys looking at. Anytime you see a molecule, let's think about what's the ratio between the two. Does anyone know what the common route of administration of this drug is? So people inject it. Snort it. So one of the really interesting things, I did a little bit of reading about it, and it turns out that people that handle the drug, so drug confiscation or dealers or whoever else, this drug is actually very fat soluble. Our skin, the barriers are lipids. So this drug can actually be absorbed through your skin, through your mucosal membrane. So if you were to touch heroin and hold the powder on your finger, there's some of that would go into your skin, which would go into your bloodstream. Which is very different from most drugs we're used to. Any polar drug is not going to do that because our skin is nonpolar, and that's a barrier for things going into your body. So we usually compare things to another. Say, is this more polar than that or less polar than that? And if we have information like, if we knew that it goes in through the skin, but we put it in water and it doesn't dissolve, we would say, well, this is going to be relatively nonpolar. So it's all a relative scale. There's no exact way to say this is a polar molecule or this is a nonpolar molecule. Water we can say is polar. Octane we can say is nonpolar. But in between there's a lot of gray area. That's a good question. Okay, so as you guys have been kind of working today, we're going to be working on a heat curve again, which is that activity that you guys looked at outside of class. I want you guys to be able to draw it, and the whole time thinking about the molecular level of things changing phases. What's happening at the molecular level? We've already talked a little bit about this, predict the relative solubility of various compounds in different solvents, predict how adding something to that solution or that solvent will change the interactions. And I think that's mostly it. Short learning objectives for today. So let's do some simple questions that kind of get us in the right frame of mind. Take about 20 seconds, click in your answer to this, your thoughts on this first question.
It says supercritical fluid. What is that? What does that mean?
That means it's a mixture of all three phases at the same time. If you Google a YouTube video of supercritical fluid, it looks so cool. It's bubbling at the same time as it's freezing, at the same time as it's melting. It looks all right, everybody clicked in? So Kirk, can you explain?
I can try. I said it was false because I remember in pre-quiz about the I don't know how to pronounce that word.
Colligative properties?
Colligative properties that when you mix water with other compounds, it can raise the boiling point and lower the freezing point. So it's possible for water to have a lower freezing point than 0 degrees Celsius.
Okay, so there's two different questions you're getting at. One is, can we change the temperature at which it changes to a solid? That's the question you're addressing. This question is even simpler than that. It's just saying, once we have a solid ice, can that ever be colder than 0 degrees? Michelle, what are your thoughts?
I would say yes, because it can get, just because it can get, it's just because it's already ice, it's going to get colder, it'll be closer hot, maybe, or...
So does the volume of ice change when you cool it down or heat it up? If it doesn't change phases, if it's solid ice, does that change volume?
The volume doesn't change, the density does, right?
Well, if the volume doesn't change, the density wouldn't change, because density is how many nuclei in a given volume.
Yeah.
So on a molecular level, what does ice look like at negative 1 degree Celsius and negative 20 degrees Celsius? Is it identical? Is there any difference at all?
I feel like there's no difference that we would notice.
There's no difference that we would notice visually looking at it. But you guys were working on that chem tour thing last night, or you looked at it. Chase?
The bonds have less kinetic energy.
The bonds, so...
Like the atoms, more like the atoms have less kinetic energy because the colder it gets.
So I like where you're going. I think we might be able to clarify that statement. So it has something to do with energy. Which one has less energy, the warmer or the colder sample? Colder one has less energy. So how does solid demonstrate having energy? Liquid, we said they're moving. The speed of their movement is how much kinetic energy it has. So how does that translate into a solid? They're not moving. They're crystals, right? They're locked into place. So how does the colder one exhibit less energy? Taylor?
Maybe orientation of how it's.
It's locked into place. It's not moving.
Would it have to do with how much energy has to be put in, or, yeah, how much energy has to be put into getting it to change state?
Okay, true. So less energy would be needed the warmer it is to get to a phase change. Thomas?
What the particles are doing slower?
Okay, how are they moving?
They vibrate.
They're vibrating. All solids vibrate. Each molecule will vibrate. It's not moving physically. It's not transposing. It's not moving to another location, but it's staying in the same place. And the colder it gets, the slower that vibration is. When does the molecule stop moving?
0 degrees Kelvin.
Yeah.
Absolute zero. That is our definition of no energy at all. Once you get to 0 Kelvin, things stop moving completely. But after that, they start, as you warm it up, they start vibrating. Once they're vibrating enough, what happens when it gets to 0 degrees Celsius? Now it has so much energy that it starts to move, and now they're no longer in that lattice structure anymore. Okay, so the density, the volume that they occupy, and the positioning of them, that is only based on what phase it is. Once you change phases, now it's a totally different game. Let's look on the other end of the spectrum. Once we convert liquid water to gas, we go above 100 degrees. Can steam ever be warmer than 100 degrees Celsius? And what's the difference if you say yes? Talk to your neighbors. Click in your answers. And we're closing out. Okay, would anyone like to take a stab or explain? Let's have some people who haven't talked. Salma. Okay, so you said that steam has to be 100 degrees Celsius because that means the water molecules now have enough energy in order to be apart from each other. So then what changes about the molecules when you heat it up above 100 degrees? They move faster. So what did this question actually state? It said never goes above 100 degrees. And that is absolutely false. The faster those molecules are, the hotter it is, or the hotter it is, the faster those molecules are moving. So what I want you guys to do now is on your worksheet, I want you to draw starting at negative 20 degrees. So we'd start over here on the left side. We're going to say we're at negative 20 degrees Celsius. As we constantly add heat, so it's a constant addition of heat from left to right, what happens to the temperature of that substance? And why does it not look, why might it look differently than, how about this? If you were to explain it to someone that's not in this class, why does it look differently than what they might expect? I want you to focus on the why, the molecular level of why.
Hey,
How are we doing?
good, how are you? Is this wrong?
Not saying it's wrong, all right. So maybe add some labels or some descriptors to know what's happening at different points.
Well, yeah, but it splits. Like it'll be like liquid or like solid or liquid on the bottom, and then it's like another
So
gas.
try to be as descriptive as you can. Go ahead and draw something in pencil. I want you to put your thoughts down. Kirk, what was your question? Sorry, I didn't come back to you so quickly. You remember?
Oh yeah, when we were talking about the number of bonds in the catalytic molecule, we said that carbon's so
It's not super polar, but
it's like not very polar at all.
Yep.
Okay,
So those are, we listed the different bonds that are polar. You always want to recognize those. That's carbon, so oxygen or oxygen or nitrogen, hydrogen, either one of those. So those are 4 bonds you always recognize. There's varying degrees of it, but
yeah, that was what I was confused, because I put 8 for that one.
so I want to see you guys draw something on a pencil. I don't care what it is, make sure you have something down.
Okay.
Is this what you wanted, something like this?
So this is a phase diagram. This is a bit different. So what we want is the one that says what. So maybe talk to Shane about the difference between this and that. Draw as many labels on there as you can.
Are we supposed to draw the point where it's like these lines?
What is that?
So then, if we do this,
So you're combining 2 completely different
so you're not
graphs. They're different things.
Okay, okay.
It's like saying speed versus fuel
Oh,
mileage.
okay, never mind. That's
They're like
pressure.
totally different things. All right, let's bring everybody back together and we'll talk about what you guys have drawn. So McKenna, when we have ice at minus 20 degrees, what does it look like? If we were to go and look at those molecules, what we're going to see? Okay, they're together, and what about their movement? They're not moving in what way? They're not vibrating as quickly. What do you mean? Claudia, you want to help her out?
Well, you're asking how is ice moving?
Yeah, is ice moving?
Yeah, well, the molecules are vibrating, but like, if you lower the temperature, they're not vibrating as quick.
Okay, so we have molecules that are stationary. They're not moving around, but they're vibrating. Okay, as we add heat, constantly add heat, what's happening to them? Are they changing at all? Okay, so the vibration increases. So that means that also the temperature goes up, right? Then we get to 0 degrees. Dan, what happens at 0 degrees? So what happens to the heat curve? So some of those molecules vibrate enough where we start to get liquid, and that slowly converts to liquid. So does the line keep going?
It's going like right now.
Say again?
It's going right, like just flat.
Flattens out? Why? We're adding heat to it. Why doesn't the temperature go up? Salma?
Is it still a liquid and a solid at that phase?
Yeah, so it's still a liquid and a solid at that phase. So then why is the line flat?
Doesn't it take energy to change it? Switch up.
Great, so it's not just about now the molecules go from vibrating. Well, that vibration now turns into a translation, a movement in physical space. And that takes energy. That doesn't raise the temperature of it. So that means it stays the same temperature. So on the far left side here, what is that sample? Solid on the far left side. On the far right side, what is it? And then, what happens after the whole thing becomes liquid? What's the next thing, Salma? Now all the heat starts to go into making those molecules move faster and faster. So that means that at 0 degrees, everything, well, it depends on where we are, how much heat's been added. If we're on the far right side of that blue line, it means now everything is liquid. They're moving around, but they're moving somewhat slowly. So we start to add more and more heat. They start to move faster and faster. The temperature goes up until when, Brian? Until 120 degrees. Does everybody agree? Demetrius? Why 100? Okay, so we know that water freezes at 0, boils at 100 degrees. So then what happens to those molecules? So we want to be really careful. When we say break apart, we think about taking a covalent bond and separating two atoms that are covalently bonded. Is that what you're talking about?
I'm talking about the molecules of water that are brought together that make them start to, like the intermolecular forces between them start to break apart and start to become water.
Okay, the intermolecular forces between them start to be overcome. That's how I would say, not break, because I don't want to be picturing water going from... Sorry, can you guys see this? Is that even visible? Can you throw me a pen from the back? This is the only one up here. I play soccer, not basketball. Didn't bounce, okay? I play soccer, trust me. Better? So, in the worst case scenario, we have people draw this when things boil. What's wrong with that? It's not water anymore, right? We're changing phases. We're not changing the chemical structure of the molecule.
Isn't the state of matter based off of like a bunch of molecules too?
Yes, good call. So it's based off of a whole bunch of them and how they're interacting with each other. But it's also defined, the molecule is defined by the covalent bonds or the ionic bonds that exist. This is not water. We can't say anything about the phase here because we don't see more than one. Exactly. Okay, so we get to 100 degrees Celsius, and then what happens? Now those molecules, certain ones of them, have enough energy to overcome those intermolecular forces. So then what happens? Thomas? Okay, so they've already been speeding up. They're already speeding up to, the average now is going really fast. So what happens? If we keep that temperature for long enough, then enough of those molecules are going to overcome that intermolecular attraction. But all that energy now is going to changing phases, to giving them enough energy to overcome that phase transition. And then what happens when all of them are gas? Alex? Once all of them turn into gas, what happens to the temperature? The more heat we put in, the higher the temperature becomes. So in this purple line, what phase is everything at the far left side of that purple line? What about on the right side of it? And in the middle? Some of both. Depends on how far we are in different directions. So I saw a lot of people draw this essential thing here. But there's one big difference. What do you notice about the length of the blue line versus the length of the purple line? I want you to talk in your group. Look at how I have it drawn. The length of the blue line, the length of the purple line. Talk within your group. And I want you to see whether you did the same thing, and if you did, if it was intentional, to describe why those length of lines are different. Don't redraw it. Don't focus on redrawing right now. I want you to focus on why one might be longer than the other.
It's longer because it takes more energy to get the molecules that long. Because I just drew it with the bottom.
Can I catch up with you for a minute after class?
Yeah, make melts ice cube to liquid, and then all melts like ice cube.
Not what? Bring the last lesson. The last lesson? What? I missed the point of that statement. I'm sure it's good though.
All right, I want to hear from someone who hasn't talked yet today, so let's hear from Sabrina. Okay, so you're talking about the amount of time, and we can talk about heat added in two ways. Either the amount of time, if it's constant heat, or we can say the total amount of energy needed to overcome that phase barrier is greater for liquid to gas. Does anyone want to expand on that? Taylor?
Well, when you're heating something from liquid to gas, I think you have to break the intermolecular forces.
Overcome the intermolecular forces?
Overcome the intermolecular forces so that it can separate. So it's going to take more energy to break, well, to overcome the intermolecular forces than to calm them down.
So you're talking about different directions, so careful with that. So calming them down would be going from liquid to solid. We're talking about going from left to right, that the blue line is less energy input than the purple line going from liquid to gas. Shane, you want to add to it? So he's teaching our next class. Does that make some sense to you guys? Then in order to go from a solid to liquid, we're just taking intermolecular forces that are static and kind of moving them past each other. We're sliding them past each other. But once we go from a liquid to a gas, they're completely obliterated. There are no more intermolecular forces, in theory, for an ideal gas. They're completely separate from each other. So that amount of energy, not only that, but we're also giving them enough kinetic energy. So instead of having gravity hold liquid down, right, you obviously liquid is not in the air, that they have to have enough energy to now be free floating and overcome gravity. That's a lot more energy that we're putting into that system. Not overcoming. We'll get into gas laws later. All right, so the next thing I want you guys to do is we're we're going to talk really briefly about these two different types of diagrams. And then I want you guys to do some modifications to the graph you just drew. So if we look at these two diagrams, the one on the left we call a heat curve. Specifically about heat added versus temperature. I want you guys to look at these two graphs. You had to do a little bit of work with the right one. Now I want you to discuss what the two diagrams share in common and what's different about them. What information can you get from one versus the other? What information can't you get from both? Join them or them.
I'm gonna join them, but I just have a better view.
Maybe you guys can scoot forward a little bit, find some middle ground. Thank you.
That's when it goes.
Let's just do it from ice. Who has been extremely quiet today? Chelsea, you haven't said too much. Do you want to share your thoughts? What can you get out of these? What's more information, less information?
Well, the right one includes pressure, and with more pressure, you get more temperature, whereas the left one doesn't include pressure.
Great. Okay, so from that I'm going to pull out that the graph on the right includes pressure as one of the axes, which means that it talks about how pressure influences what?
Different stages of turning ice to gas.
Great, the different states. So the state is somehow influenced by pressure. Why does that make any sense? Can you guys picture that in your head? What is pressure? What does it look like? Show me with your hands or describe it. Okay, so everyone's pushing things together, right? So if things are in gas and we push them together, what does that mean is going to happen? So this is kind of talking about that somehow by squeezing things together, we change what happens. So with water molecules, which is more dense, ice or liquid water? What floats? Ice floats, so that means it is more or less dense? Less dense, okay? So if we take ice and we squeeze it together, then what happens? So if we take ice, let's say we have ice at this temperature, and we squeeze it together, we increase the pressure, at some point we force those molecules now to be liquid. So there's some relationship between pressure and phase that one on the right shows us. The one on the left, does that have pressure anywhere? No. Okay? So what are some other observations between these two? Justin?
The one on the left shows more of a progression over time between the phase changes.
Okay, so it's not just time. It's how much heat is added per time is that bottom axis. So if... Go ahead, Chase.
I was just going to say something different.
Go.
Point of the molecule? No.
So the one on the right shows a triple point where all three phases exist, which is crazy. If you haven't seen that, go on YouTube and search for a triple point. It's really cool looking. And then go back to Justin's point here. If we're at atmospheric pressure and we have solid ice and we warm it up, we're going to heat this up, not changing the pressure, we can find the temperature at which we change phases. What information does the graph on the left have that one doesn't?
How much heat was added?
how hard it is to overcome this barrier. The one on the left tells us how much energy is required to overcome that. The one on the right doesn't. It just tells us what temperature it happened at. So the graph on the left, if pressure is not included, then what do you think pressure, how does pressure play a role in that left one? Is that a vague question that's not really useful?
Specific pressure for each graph. You have to change the graph. You have to change the pressure.
That graph on the left is only for one very specific pressure. That one on the right shows all different pressures. So there's things we can gain from both of these. The one on the left is at one pressure, but it talks about how much heat is required to overcome the phases. We can go across here, and we can say, well, now we're boiling. How much energy does that take in the right? We can't tell. We can keep going. But we can tell what temperature different phases are at different pressures. And so this is actually some of the discussion about climate change. How do we get rid of CO2 in the atmosphere? Well, some people say if we compress CO2, we can make a supercritical fluid, which means it's liquid under very high pressure. We can bury it under the ocean. It's all kinds of crazy things that we're doing here.
So if we start from like the lowest one on the right graph, it's saying that you can go from ice straight to water vapor.
Have you ever seen a substance that goes straight from solid to gas? What? Dry ice. Exactly. The same thing can happen to water if we're at a low enough pressure. So there's a couple different interactives here. That top interactive is the one I sent you guys. The bottom one is a simulation that lets you play around with these. Morgan?
So I'm just trying to overcome the concept. When I think of ice, I think of something really cold. So how does when adding, I'm just getting over like that whole ice and water, like how does it change like with a certain amount of pressure without a temperature change necessarily?
Well, so none of these are warmer, much warmer than the temperature you're used to. It goes up to 0.01 degrees Celsius. So it's really colder temperatures. Now it can be a liquid. So the bottom of the ocean, or bottom of a lake, if we have a really, really deep lake that's fresh water, then even though it's below 0 degrees Celsius, because there's so much pressure, it can't form a solid. So that's what this graph on the right tells us. So let's look at that graph that you guys just made, and I want you guys to hypothesize what that heating curve would look like, what differences there would be if now instead of having pure water, I want you to say this is what it's going to look like if we had sodium chloride or salts in that solution. So draw a second curve on top of your curve that you already have. And I want you to intentionally compare what you have, and I want you to think about why. Maybe do it as dotted lines so we can see the difference.
What? Yeah, higher temperature. I think it has, I think it has a higher boiling.
You guys only have 2 more minutes. This is a quick activity. Hurry up, write something down. Get something down on paper. No, but I want you to just get this off your head, and we're going to come back to it. What are you thinking? Just make a guess. Try to draw something down if you can rationalize it.
I think that's exactly
1 more minute. Make sure you have something written down, and then we'll come back to it. All right, let's move on. We'll be coming back to that, so don't worry. So So this brings us to what our lab is going to be next week. Your studio tomorrow with Miss Terrell is going to be on this as well. You're talking about what happens when we dissolve something in a pure substance. So let's make sure we got our terms down. If we're going in that magic school bus view, we're zooming all the way in. We're seeing each individual thing as a dot, whether that be a molecule or an ion. This is what we're going to see on the molecular level. So we have a mixture here. In this mixture, which one is considered the solute? And why is it the solute? A couple more seconds. Alex, which one did you choose as a solute and why?
I said the red one because the black circles are kind of shaping it and like breaking it apart. So there's the red circles.
So careful, we can't describe what's happening between them. What's our definition for solute versus solvent? Kira?
Solute is what's being dissolved, and solvent is what's doing the dissolving.
Okay, so that's one way to think about it, but there's a more technical chemistry way than what's being dissolved, what's dissolving. Cosme?
And also what you're adding. Like if you add something, it's usually solute.
Not necessarily. It doesn't necessarily have to do with what you're adding. What's the strictest definition?
I don't think this is right, but I'm going to say what the solute disassociates and then the solvent does the disassociating. I don't know.
That can be the case, but not always. Don?
Is the solvent polar and the solute non-polar?
Completely depends. Has no defined polar or non-polar. Salma? So one is in a greater quantity, that's the solvent. Usually that's water for what we do. Next week in lab, it is not. Next week in lab, that's stearic acid.
What do you call either of them if there's an equal amount?
Then it's semantics.
Okay.
If they're even close, semantics. But really we're saying the one that has more molecules or ions or particles or whatever, that one is going to be the solvent. The one that's in lower amount is the solute. And that's going to be really important for our lab that we're working on. So, thinking back to your fracking activity, we were trying to get methane out of the ground fracking, right? Which one is a better solvent to dissolve methane? Question?
No, I thought you were asking.
A couple more seconds. Closing out. Natalie, which one do you think would be a better solvent for extracting methane?
I said octane,
Why octane?
because it's nonpolar, and methane is nonpolar.
Great, so we saw the methane's nonpolar, octane's nonpolar, so not much of it's going to dissolve in water. But then the question was, if we're actually going to go out fracking, are we going to inject octane into the ground to get methane out? Why not, Brian? Okay, so one, it's hazardous. Good point. Two,
We don't want to dissolve it.
we do want to dissolve it because then we pull the fluid back out and now we have it. Why is it a terrible idea to inject octane into the ground? We have to extract it in the first place and purify it, and then we're going to inject it back, and it's stupid, right? So what that activity is getting at, if you guys go back and complete the rest of your fracking activity, is thinking about why we're going to use water, and then there's a whole bunch of other questions in that packet that get into the intermolecular forces. Although it's not ideal, it's a little bit soluble. There's a little bit that goes in. And is that enough? So there's a lot of kind of applications of intermolecular forces to what we choose to do, where we choose to do it. So there's a lot of policy that's involved in that activity. So if you haven't completed it, I highly recommend doing that. So the next set of questions, and actually let me, before I put this up, big picture, colligative properties for the next section we're going into. Question is, that graph you drew, what should it look like? Two major factors we need to consider. One, does something dissolve? Why is that the first question we need to ask? Why is the first question we need to ask, does something dissolve, before we go any further? Jose?
If it doesn't dissolve, then it's maybe, well, if it doesn't dissolve, then it's, have like higher boiling points. It's not, like, what's not a part of the solution. It's all it's going to be at the top of something, and there's going to be a lot more tension and force there.
Okay, so it's going to be something that's either sunk to the bottom or floating to the top. It's not going to change the intermolecular forces that are there. Okay, so step one, you guys need to be able to look at a compound and say, does it dissolve? If it doesn't dissolve, we don't care. Irrelevant to any colligative properties, okay? Then the second step is, well, when it dissolves, what influence is that going to have on boiling point and freezing point? So that's where we're going with this, and that's what your studio tomorrow is going to be heavily involved in. So let's work on that first one. Does it dissolve? Which of these two solvents is going to be better to dissolve this compound? And I better, sure, see you guys doing something I'm telling you need to do. All right, let's do about 15 or 20 more seconds. All right, closing out. What did I want you guys to do? How about you draw the Lewis structure? What does it look like? Pat.
Double bond to oxygen up top, and then a single bond to an oxygen on the one side, and then single bond to oxygen on the other side.
Great.
And then there's negative charge on each of those single bond and oxygen.
Okay, great. And then what's the rest of the structure that we don't have up here?
The lone pair.
Okay, as well as the lone pairs. Okay, so what's the first thing that we look at? Thanks, Devontae. We look at this and we think immediately. Anybody?
Polar.
Not even polar. It's ionic. It's like even more than polar. So what's that going to dissolve in? Okay. Is it going to dissolve at all in octane? No. That would just be sitting at the bottom of octane. It would just stare at you and do absolutely nothing. So that one person, I hope that you guys talk to me about that after class if you're having trouble with this. What about this compound? Does anyone know what compound this is? Yep, cyanide is 1C triple bonding to nitrogen. All right, so has anyone not talked up in class today yet? What's your name? I'm sorry. Dana. So Dana, what do you think this is going to dissolve in? Better. Why octane?
Because it has more non-polar.
It has almost all nonpolar bonds. It has 3 polar bonds, but they're carbon-nitrogen, which are some of the lower polarity of those bonds. What is this molecule? PCP. PCP is another compound that if you handle with your fingers will absorb into your bloodstream. But the really interesting thing about nitrogens is they have a lone pair. And if you put them in contact with an acid like HCl, then they form an ammonium salt. That means the nitrogen has 4 bonds to it. What happens to nitrogen with 4 bonds? positive charge. So now PCP is an ion. So one of the ways that this drug is administered is as the HCl salt. That makes it more soluble. That means it can go into your blood and dissolve. Okay, so when this drug is used recreationally, that's how they get it into the bloodstream. So does anyone want to explain where the H goes? So if we had drawn the full Lewis structure of the left PCP, we'd have a lone pair there. If we have HCl around, that lone pair will grab the H+, and then we have NH with a plus, and then the counter ion is Cl-, and that's a salt. Bailey?
How do you add, like, atoms and stuff usually becomes like a different molecule? How can they take?
So it's a salt, and if you put it in water, it goes back to what it originally was. So yes, the ammonium is technically a different compound because there's another covalent bond. I agree. But it's one that is easily interchanged. It's the conjugate acid of a base. Any nitrogen with a lone pair is a base, so it's the conjugate acid. So yes, it's a different compound. All right, let's look at this compound. Anybody know what compound this is? Or what category of compounds this is? It's a lipid-ish compound. What's that, Shane? Fatty acid. Why is that more specific than a lipid? So where's the fat? Where's the acid? Fatty acid says that you actually know your functional groups, and you can see there's carboxylic acid. Okay, so go ahead and click in your final answer. Closing out. Wah, wah, wah. It's not really going to dissolve in water, but it has such a polar head group that it's not really going to dissolve in octane. So what happens is it actually forms micelles or lipid bilayers. So the tails stick together if it's in water, and then the heads are exposed to water on both sides. Or it forms a ring. If it's in octane, all of the carboxylic acids would be in the middle, and the tails all stick out towards the octane. Forms three-dimensional structures. So this is stearic acid. This is the molecule you guys will be working with next week. Does this look like a solvent? Not like a normal solvent we have, right? It's not water. This is your solvent next week. This is the one that is going to be in molar excess. All right, I want you guys to tell me which one of these is most water soluble. And I want you being very specific, looking at the different molecules. I like drugs. More interesting. All right. What are we looking at here? Let's talk through this. We have about a minute left in class. And by the way, Thursday's class and tomorrow starting in studio, you guys are going to be doing a lot of calculations with molarity, molality, percent mass, mole fraction. If you guys don't remember, especially molarity, go back and do a chem tour on that. Under the chem tours, there are molarity and what that means. And there's a molarity Pogel activity that you guys have already done if you're in our class, so go back and do that. So what are we looking at here? How do we tell which one of these is most water soluble? Do you notice any similarities in these? Demetrius?
You're just looking at the ratio between the non-polar and polar bonds.
Okay.
Whoever has the highest amount of polar bonds.
Highest amount, but not only amount, right? That not every polar bond is equally as polar. Which ones are the most polar that we're looking for?
The highest ratio of polar to non-polar.
It's not just the number, the ratio. Taylor?
The one that, like, OH is, like, really cool.
So if we see an OH compared to a CO, we know that's going to be count for more. So if we had a carboxylic acid, then that one would win out by far. We don't. We have an alcohol, which is the next most polar functional group. Do you guys notice any similarities in these compounds? Can you see why if someone was given morphine or codeine, why heroin would be a next step if they're addicted and they needed to get more of that drug. So it functions a little bit differently in our brain, but overall, these class of drugs are all based on the same scaffold, and that we prescribe these drugs. We overprescribe the hell out of these drugs. So I actually found out that heroin is actually prescribed still. Do you know that? It's prescribed as a painkiller. In the US, in the UK. It's called dimorphine is the name of it when it's prescribed. But I don't know, some food for thought. So last part, absolute. I know. Damn it, I'm over time. I'll just leave you guys with this, and I'll say that. Quick. The sodium chloride. Which one of those two is sodium chloride in water? Blue. That's not what a lot of you drew. So before class on Thursday, I want you to think about why both the freezing point goes down and the boiling point goes up. And read in your book if you want some answers on that. Anything else? Thanks for your patience, guys. Great job today. We actually got through all the class that we wanted to. And remember, this is what I wanted you guys to be able to do.